Okay, so welcome everyone. Today is the first session, so it's also like a pilot session of the Quantum AI Lab Quantum Simulation track. Yeah, please, Omar, if you have any announcement, please proceed. Please also inform them also in the chat and also speak about it.
Yes, please. There will be a WhatsApp group for the one joining the Quantum Simulation Lab. So if you haven't registered yet through the form, just take a moment to register and come back. Thank you.
Thanks, Omar. So we have here a few colleagues from our community who are joining the lab. Also, we have Abdurrahman Al-Said, he's the coordinator of the Quantum AI Lab, Quantum Machine Learning track, and Ziad Tariq is the coordinator of the Quantum Simulation track. And we have also Omar Sobhi is also the coordinator of the various activities in the community, and also Muhammad Fergani. And we have also Ahmed Saad Al-Fai, and I believe we have one extra name, but maybe I don't recognize it from the list. So, okay, so welcome everyone. Today is first pilot session of the Quantum AI Lab Quantum Simulation track. And in this track, we are going to explore together quantum simulations and how we can use the tools to facilitate and design a quantum simulation. Quantum simulations application is very active for companies, but also for the industry, for research, and for many other applications. And the trick in this field is about how to design a correct simulation that reflects what you see in the lab. So when you make a design for a quantum processing unit or simulate a molecular structure, or even synthesize a new medicine, then the simulation has to reflect this in a correct way. So you need really to have a very accurate quantum simulation. And there is a variety of tools to use this. There is also numerical tools, computational tools, and also the variety of algorithms. And all the synergy of this gives us a rise for the quantum simulation. Today, we are going to explore fundamental aspects of quantum simulation, which is about the numerical integration, why we should use it, how we can use it, and how we can benefit from it in quantum simulation. Numerical integration is very essential role, despite the fact that it might be tedious or obvious for some of us. However, it is very crucial and a very crucial step for quantum simulation. Sometimes a very nice simulation might fail because of a very tiny mistake that happen in the way that you compute the coefficients using numerical integration. So typically we use numerical integration to expand or to express a function, so to represent a function on a sphere or for anything, so we can have an analytical representation of this function or this data. And using this analytical representation, we plug it in our simulation. I'm going to share my screen, so at least this has become visible for us. Okay, so hopefully everyone sees my screen. Is it the case or not? Yeah. Okay, so hopefully it is visible then. So numerical integration or numerical integration methods are very important for like solution of ordinary differential equations, partial differential equations, and also giving analytical solutions or representation for what we think it could be analytically represented, like a potential energy surface in chemistry. typically we need to represent the angular part of this potential, which is very crucial in physics and chemistry simulations, using spherical harmonics. We are going to explore what the meaning of spherical harmonics and how we can use them to represent the different molecular orbitals, but also to have a way to define or represent data that are given to us that's distributed on a sphere. And spherical harmonics is a famous function that can do this. The main trick in quantum simulation is a choice of the proper representation or the proper kernel where you do your computations in. So the choice of coordinates and also the choice of the expansion functions, how you want to represent your data analytically. So which type of function you can use. So for example, in machine learning, sometimes we use sigmoid functions, different types of functions because they are proper for this particular kernel. Similarly, in chemistry, because there is symmetry and interaction potentials, we can use function like spherical harmonics, and spherical harmonics are famous for this. So the spherical harmonics here are functions of theta and the phi. Those are the polar coordinates, of course, of spherical coordinates, and they are denoted by two numbers. We have the L and the M. The L represents the L and the M. They represent different moments and degrees and order of the spherical harmonics. We are going to explore them later on, but the take-home message here is that we see here a part that's in phi and a part here in theta, and we have the normalization part here. So typically, if you are given data that's, for example, are a product or computed by this function, then we can expand this function or represent them, the data from this function in terms of spherical harmonics using spherical harmonic expansion. So we can have a kernel or a representation in which all the terms from spherical harmonics times a certain coefficient, if we sum them, where L, which is a moment of spherical harmonics, goes from 0 to infinity, and M, the degree we have from minus L to L, if we sum all of this at theta and the phi, we get the value of the function at this particular point of theta and the phi. So now we have a representation. We can make a representation. So instead of having sine theta and the cosine phi like this, plain sight total function given to us like this, we can expand it using spherical harmonic terms. So we can have different terms to add or to benefit from this expansion. Why we do this? Because it is very crucial for interaction potentials to represent or to define couplings in different terms. So each spherical harmonic function have a certain shape or a certain property in space. So it takes certain shape in space. So it defines a certain interaction in space. So maybe you are familiar with the molecular orbitals. They are coming from, or atomic orbitals, they are coming also from spherical harmonics. So the main goal of the next session, which this session is a foundation for, is how to compute this expansion coefficients CLM. Stands for complex because this is a complex spherical harmonics. We have different types of spherical harmonics that we are going to see them later. And these different types could be real, sometimes because we take a superposition of complex ones, or you could have different normalization. However, this is just the main complex, fully orthogonal and fully normalized spherical harmonics, and the goal is to find this coefficient, and typically these coefficients are computed with numerical integration. So you see now we make an integration. This integration cannot be carried analytically easily, so the only way is to set up a grid of theta and the phi, and from this grid we can compute these coefficients. Okay, so this is the main goal. We wanted to keep it in our mind, and today we are going to explore simply the foundation of this, and next time we are going to apply this as well, of course, with depending on the progress that you are going to do with my colleague Ziad here, who is going to take care of the laboratory session. Okay, so now if we are given a function we would like to integrate, the obvious solution is to go with the trapezoidal rule, and the Trapezoidal rule is a way that to make a numerical integration that can approximate an integral or a function just by dividing this integral or integration interval into small sub-intervals. So you are like dividing, having very small pieces of things. If I share the screen of my tablet, I can also highlight it quickly. So you can have, for example, any given function like this. The trapezoidal is sort of, you are making really tiny sub-intervals like this, and then you sum all of them in order to probe the area under the curve. Of course, this is like a delta x, so depending on the size of your delta x, when you make it smaller, and also the number of points you use here, you can make your integration much more accurate. Feel free to stop me if you have any question. So this is the main formula. So you make a segment between, if you want to integrate a function on interval from a to b, then this function, you subtract b minus a, and then you divide by n, and then sort of you get this pairwise points. And from that, you can approximate the integration that you have. It's very straightforward formula. You approximate the function, you evaluate it at xi, and then at xi plus 1, you divide by 2, and then you multiply by the step. And then if you sum all of that, then you sort of get an approximation of your function. Okay, so I can make a quick demonstration. Okay, 1 second, my notebook will be open. Okay, so I'm using Julia. So hopefully you are all familiar with. Who is not familiar with Julia? Please raise your hand. Okay, so we have all. Okay, so we have brave. 2 persons are brave. Okay, the rest are excellent. Maybe they are experts in Julia already. Okay, we have 3 brave persons. Okay, and then we assume that the rest are already expert in Julia. Okay, so more are coming in. You know, might ask Ziad to cancel the review session of Julia and step in directly into the programming part. Okay. Anyway, so let's run these libraries because we are gonna need them. So it's a different way of calling, like importing libraries in Python, but they are just done differently. Okay, because I've already installed this one, so I don't need to install it anymore. Okay. Then now the first thing which we can try is that let's make a function like sine, for example, and then let's plot this function. Okay, so we're all familiar with the sine function. I mean, it's very simple sine function over half interval. So it goes from 0 to pi. Okay, now the question is, can we use a trapezoidal rule to integrate it? We have seen the formula. So there is nothing magical about it. We can just define it. We define this function of the trapezoidal rule. We execute it. Then we have it ready in the memory. So Julia is fast because it's a compiled language. So you can compile the functions on the fly in the memory. And if you have it, then it's in the beginning, it's very slow because after the compilation, it takes time to be compiled. But then you have like a virtual image in the memory about this function. So when you call the function, it's becoming super fast. So Julia is like a hybrid language. It's still a script language, but it's very hybrid, very optimized, and sometimes have Julia has a very close performance to low level or even very efficient programming languages like Fortran. So now let's make this approximation and we can see what happened. If I do like this, then I can see that this integration, the exact value of it should be 2, but I still used 10 points and then I didn't get 2 exactly. So if I'm doing a numerical simulation, I need to get a very good precision of this coefficient, of this integral. So it has to be 2. So, okay, we are all familiar with that. We have the trapezoidal rule. We have implemented the formula here. We choose this step function or step size, which is a half. And then we multiply it by the 2 points, the function evaluated at A and plus the function evaluated at B. And then we do this basically compute the integral by summing all of these tiny intervals, and then we get the approximation. We can also make a plot at different points to see the behavior. Then if I run this loop, I can also do a plot here. This loop will just loop over different numbers of points. Yeah, because that function has been already defined. Let me isolate it in a different cell. Where is the exact integral? I didn't define it because I don't need it here. Okay, let me just put it here as well. Okay, so now what I did plot is that I use different number of points. So if you have 10 points under the curve to represent these trapezoidal intervals, and you can have 100, 200, 500, 1000, 10,000, and then even 100K of points. And then you see, okay, you still have some fluctuations, but around 100, the function has been converged. So the integration has been converged after 100 points. So you need 100 points in order to get acceptable level of precision in quantum simulations if you use the integration using a trapezoidal rule. Okay, so we have a method that works out of the box. It's very easy. You make a sort of rectangles to probe the shape of the function and the area under the curve. And then you sum all of these little areas. And then when you sum them, you probe the shape of this function, and then you get the integral. So far, it sounds easy, right? Okay, so I see Abdurrahman is raising his hand. Yeah, please, Abdurrahman, please go ahead if you have a question. Okay, I see Muhammad is raising his hand. Please go ahead. Your voice is still away, Mohammed. Yeah, that's a good question. So here, what we do uh, is precisely this. We increase the number of intervals. So n values is actually the number of intervals. Let me not go through this very quick. I'm just gonna share the tablet screen again, just quickly. So the n here is actually this point. So the number of this number of points. So if you use, for example, 3 points, this is your function, then you have only almost 4 intervals, 1, 2, 3, 4. So when you increase the number of n, your intervals become very smaller, and then you probe this shape much better, because this is like you get this area of triangle of rectangles, and then you sum them. So when you squeeze, you increase the number of n, then this rectangles will get smaller, and then they will probe the shape of the function much better, and then your approximation or your solution will become much better indeed. Okay, so I see a question from Abdullah. Please go ahead. Okay, so did this answers your question, Mohammed? Okay, thank you for your question. So now that's what we have. Please feel free to ask, because this question is very nice. It also highlights or sometimes slows me down if I assume you get it quickly. So that's the idea. So we all now have seen this number n. If we do with this number n, we increase it. We sort of probe more or add more, squeeze more the rectangles. So we make their areas very small, so they can probe the shape of the function. So this is a main idea of this integration. Can I probe the behavior or the pattern or the shape of the function with this method? And if yes, with how many points I can use? So now that's our idea. So I use here 10, 100, 200, 500, 1000, 10,000, and even 100K. So, and from that, we end up with this. I plotted it on log scale just to show you the difference. So here it's 100, here is 10,000. So almost the integration is increasing, increasing, the approximate integral increasing, and here sort of saturate. So we call it convergent. So we have here a precision that want to get accurate. So maybe at 1000 we will get the good result or identical result up to 16 digits of accuracy. That's what we care in chemistry or in simulations. How much precision do you have in your calculations? It's very important to highlight this, because sometimes you might not care much about the precision. Sometimes in some problems, you care more about the shape of the function, the shape of the potential. You care about the gradients of this. So the shape determines for you the gradients that you might use, the force constants, the Hessian of the matrix. So in that sense, you might not care much about this because you care more about something different. However, sometimes the gradients will be accurate when you have much more precision. So you have more accurate and the more digits in your computation. Okay, so far here is good. Okay, so feel free to stop because once we go to the advanced functions, yeah, we cannot step back to this, so we have to move forward. So sometimes it's the basic idea, but it is very crucial to understand it properly and correctly to move forward into the higher applications. Okay, so now we have this. Okay, that's nice. No, this is something which is no-brainer that we can have. Now let's see another function. So I'm gonna make a function, a polynomial function. Then I'm gonna plot this function. So, okay, this function has been plotted from 0 to 10 in steps of 0.1. Okay, it's a very normal function. We plotted it. You can plot it with MATLAB, with Python, with any language you are familiar with. It doesn't matter. What you have here is a function that's plotted from 0 till 10. Okay, it's a polynomial. Then if we use the same method to make this integration, we can for sure use this. So we can make something like this. Also, the number of points, which is the number of these trapezoidals below here, and that's what we have. So I see a question from Ahmed. So you can please speak about the question in the mic.
Okay. Good evening, Dr. Tal, and how are you?
Yeah, good, Dr. Ahmed. How are you?
I was asking about is there is a trade-off between for the number of points we use for this integration?
You mean a trade-off in the terms of how many points you would take and how many you ignore, basically, or to which limit you stop?
Yes, the limitation and the cost of the computation and simulation. So we have some limit for the number of points we can use.
So that's a good question. That's a very nice question that will come in the next slide when we come to the numerical integration by quadrature. Because of this limitation, we have to use more efficient methods.
Good to hear. Thank you.
But thanks for the question. That's also a nice warm-up indeed. Okay, so now we have another function, which is a polynomial. It extends from 0 to 10, and we have different number of n values. It's very easy method. It is very cheap, so you can compute any numbers you want. I can even put 10 million, and it won't matter much because you can evaluate it in a fraction of a second. So if I exclude this, then I get the approximate integral, and then the approximate integral becomes smaller and smaller. But then, yes, around maybe a few hundred points, your integration is sort of saturates. So the result saturates, and then you sort of your integration is convergent. So you can say, okay, now I have the good value of what I need. Then we come to the question which Ahmed has asked about is the precision of the number. So do I have acceptable precision or not? Yes, okay, that's fine. Not maybe if it's a cheap calculation, so you can add many points as you want. Okay, so far we see a very direct, very simple method for integration. So it's a very direct method. Anyone can use it out of the box. It's very cheap. The points are, you can compute it very easily. It's no brainer in this method. However, the magic only comes when coming to Ahmed's point, because that's a crucial part of this session. When you cannot have this much number of points, you cannot compute few hundreds of points in order to get good numerical integration, in order to get your expansion coefficients properly of the function representation of your given data. So in simulations, you want to have your given data, you need to have very accurate coefficients, which we have seen in the slides. I'm gonna share them again. So if we back to this, we see in order to compute these coefficients, sometimes it's very expensive computation to have the function evaluated at theta and phi. If it takes few minutes, that's fine. Then you can compute 200 points in few minutes. But sometimes in quantum simulations, especially in quantum chemistry, where the level of theory that you might use can be expensive because you explore all of the probabilities and all of the wave functions in the Hilbert space. So your computations might be expensive because you have to treat a lot of bases. You use larger bases to probe the electronic properties and have more accurate potential. So in some methods, one point might take few days. Then you don't have this luxury, or you cannot be luxurious anymore about having at least few hundred points in range evaluation in order to get this expansion coefficients, which is very important, which is are important. Of course, the theory is important for quantum simulation, but these expansion coefficients are particularly important to describe your data when you construct Hamiltonian. So in that sense, we come to the topic of today, which is integration using quadrature points. So do you hear me clearly? Is it sound clear from my side or not? So okay. Okay, so maybe I can switch just a few seconds. So I can switch. I can change the mic. Okay. Yes. So yeah. Yeah, technologies are not reliable these days. Okay, so how about now? Is it clear now? Okay, then we back again to our fancy business. So thanks, Abdullah, for pointing out to this. So we have here the method of integration using quadrature points or quadrature methods. And the idea of the quadrature is that you can have the ability to integrate a function on a specific or given interval from A to B just by evaluating this function on a particular point in this interval times some weights, some weighting factors. So if you do this evaluation, you can approximate the integration of this function and get it exactly as the analytical solution might give you or can give you. So you will get so close to this exact solution that can be computed from the analytical integration or analytical methods. Okay, so this is why it's called by quadrature. Quadrature is like you have a specific points where they have a unique properties, which we are going to see now. And then once you multiply the function that's evaluated on these points, then you can approximate the integration. So the numerical integration using quadrature schemes could be Gaussian quadrature, is also widely used in quantum simulation. Most of quantum simulations are really based on numerical quadrature methods, because in that sense you can compute the coefficients that you would like to have. And this means that any integral of any given function can be computed exactly as a sum of the values of this function evaluated at a set of specific points called quadrature points times pre-calculated weight factors. Okay, so I'm going to highlight this, how this is done. So in that sense, this figure if you want to use quadrature, you don't really use this extensive number of n's to evaluate. You only evaluate the function at a specific points. This we call the quadrature points. For example, at 3 points, then you multiply the function that's evaluated here times weighting factor. So this is the weighting factors here. If you sum, you get this integration. So you see, with few number of points, you can get a precise value and a very nice approximation that close to the analytical solution of your given function or your given data if you want to expand them and get these coefficients that we have seen before for, like, for example, the spherical harmonics. So first example is the Gauss-Legendre quadrature. Gauss-Legendre quadratures are very famous methods to be used in quantum simulations. And we have Gauss, they are inspired or they coming from Gauss-Legendre polynomials. And these are set of orthogonal polynomials, so they are orthogonal to one another. And this is arise in the context of numerical integration. Of course, these are defined in the interval from -1 to 1 because they also based on like cosine and the sines. So they are emulating this. So they are polynomials, but they are defined from -1 to 1. So they could be used to probe sinusoidal functions. And of course, the nth Gauss-Legendre polynomial, denoted as Pnx, has n distinct roots within the interval. These roots of this polynomial, the roots of this polynomial, would serve as quadrature points for Gauss-Legendre quadrature. And this would provide an efficient way to approximate the integration. Here we see the recursion relation to generate this polynomial. So the first polynomial is 1, so P0 of x is 1. P1 of x is x, then you can use the recursion relation to generate any higher degree polynomials of Gauss-Legendre polynomials. This is a general form of Gauss-Legendre polynomials. Of course, we have to be careful here about the way that these things are defined. So here that's defined from Arfken. Typically, when we do quantum simulations and also in Molkit package, we have an open source Julia package, which all of these things have been defined with respect to certain convention. We use a book from Abramovich, and Abramovich has like a very thick book, like the godfather of the numerical methods and also special polynomials. And this book has a very concise and also very specific way of defining the polynomial. So it has an exact or a very specific convention. And typically we use this in theoretical chemistry because theoretical chemistry is like theoretical physics, but you add group theory and also advanced math and computer science. You blend all of them together. Then you get quantum theoretical chemistry. And that's very sensitive to the way that you define the polynomial. So this is defined from Arfken. That's also mentioned on Math World and Wolfram. So you have to pay attention when you look to this formula in different books. Okay, so our role now is to give an example how to use this quadrature method in doing approximating for the integral that we have seen using trapezoidal method. Okay, before going to the notebook, does anyone have any question? Yes, thanks, Muhammad, for the question. I can just share the slides again. You mean this one in this slide? Or this one? Okay, so this is a polynomial. We have here a closed integral. It's of course we have our variable here is t, so it's t, and if you evaluate this polynomial, so you have 1 minus 2tz plus t squared to power minus half, then you multiply it by t minus n minus 1 dt, you get this polynomial. So typically these polynomials, they have this shape. Let me show you the shape, why this is of a particular interest. Just copying the link. So if you look here, this is exactly the Gauss-Legendre polynomials. So the P1 of x is this straight line. P2 of x, you see, is like sort of flipped shape of quadratic function, which is like a bit of an open sign. Then you get a wavy at B3, and the B5 you get this shape. So you see it's like this polynomials expands and spans a space, and this space you have a particular harmonic shapes in it. So the solution by this came from a specific solution for certain equations, which we might explain next time, but we have, of course, to show the formulas. And then if you do the contour integral of this one, so this closed integral, and then you get these polynomials. So if you, for example, you replace z by x, then you can tell, okay, I wanted to get the integration for this contour polynomial with respect to at n equals 0. So this n equals 0. Then suddenly, if it's 0, then you get 1t. So you have a t here. And then if you make this evaluation, then you get x. Then if you do with p0, then you get 1. So that's a solution. And then if you go higher, then you get sort of alternating terms. The only way that to see here is that here you have x to power 3x, so the x square is missing. Here you have x4, x2, and x1, so x3 is missing. So there is some alternation in patterns, and this alternation in patterns emulating or gives you the rise of these shapes. Of course, this is solutions for Legendre differential equation. So if we go to a different tab, these are the solution of this equation. So if you solve this, you have L times L plus 1. Then in this solution, you get this nice special polynomials. This one deserves a session on its own, because you see here there is one fundamental thing. We will touch it later, not now for spherical harmonics. You see L, and of course, when we go to the solution, the spherical part of solving the Euler equation or Schrödinger equation, we're gonna get this L as an angular momentum. So it's not here. This is a sort of a typical Legendre equation, but when we see it later from when we make a solution for example, Schrödinger equation for hydrogen atoms, then you get the spherical harmonics as a solution for the angular part. So that's to keep in mind. Okay, so this is Legendre differential equation. It's very fancy because it has 1 and x square, and it has also L times L plus 1, and with that one you get these points that are defined from minus 1 to 1. Okay, so typically we have very special polynomials, but the only way to get meaning out of it is to use them in a use case. And typically when this used, they used n probing shapes that, for example, leveraging sine and cosine. And if we do this, we can sort of probe the shape or probe this behavior. Okay, so hopefully that yes, sort of make it close to you. I mean, unless you need anything else, but then that has to be checked from the ways that these differential equations have been solved. Okay, it's always fun to see how these solutions are coming in. So typically in exams, they ask you to how to solve this equation and to write this assumption, which you can generate different recursion relations and optimize the solution. Okay, so back to our story. So for the sake of time, we have here our notebook. So I'm going to now define the Gauss-Legendre quadrature method. So this is a function. I'm used it to define. So this is how the quadratures are defined. Then if I do this, the function is defined. I use the library called the Gauss-Legendre. You will find also a similar library in Molkit's package with the correct convention. Here the convention is not, the function is not sensitive to convention anymore. However, when we come to spherical harmonics, there is a lot of sensitivity for this because it depends on how you define the solution. Do you define with active rotation, do you rotate counterclockwise, or passive rotation with clockwise rotation? So that might even give very wrong states if the definitions are not done properly. Okay. Then now we can make a test. So if I wanted to see the quadrature methods, if I make like this, then I get the quadratures here, the roots of this polynomial at n equals 3. So for n equals 3, I get the quadrature points, 3 points here, minus 0.7, and 0 and 0.7, and these are the weights associated with them. So the whole magic will come here handy, because if I wanted to use, for example, trapezoidal rule, then I will need few hundred points to approximate things. But if, for example, I want to use, let me just get a function. Let's see if I evaluate this function. I'm now evaluating a function which is f of x equals e to power x, and I'm now integrating it using trapezoidal rule. And you see here also the integration has converged at a few hundred points. So it's still very expensive. Let's see now how it behaves if I used Gauss quadrature method. Okay, so with 3 points only, of course, the one that we have used here, this minus 0.77 and 0 and 0.77 times these weights, with only 3 points, I get almost the exact values. If I share the second screen, these are my quadrature points. I've used them to evaluate the integration of f of x equals x e to power x over the interval from -1 to 1. Then if I do this computation, it means that I have to evaluate from -1 to 1 e to power x dx. That will equal approximately the sum for 3 points, because I'm now evaluating over 3 points. So I have to evaluate the function at x1, x2, x3 times the weights. If I do this times the weight, then I get 2.3504. And the exact value of this is actually 2.3504. So you see, with 3 points only, we got almost the exact value. Can anyone explain why this is the case? Of course, I'm gonna delay it to the end. You are gonna see with Ziad more examples about this. But yeah, just to keep this question in your mind, because in 5 minutes we should explore it together. Okay, so that's nice. With 3, we got almost an exact solution. Let's try to increase the number of quadrature points. So if we use 5 points, then we have the same. So we see the value almost converged. So with low number of points, I can get the value of numerical integration. Why is that? Again, we're back to this point that in some methods where you want to compute a point, this point that you want to compute in a quantum simulation, the computation by itself of your data is very expensive. So you need to be wise about which points you want to compute. You will not compute 200 points and stay for 200 years for your calculations to finish. You need to be mindful about the number of points and the type of data that you would like to include in your simulation in order to get a good expansion, the good representation that makes you or helps you in designing the mathematical framework of your quantum simulation. Okay, so far, that's the essence of numerical integration by quadrature methods. Special polynomials are solutions that come in from particular type of differential equations, where every differential equation is studying a particular behavior or pattern, and the solution of this gives you the behavior of this pattern, how it looks like. So, for example, if you solve Schrodinger equation, you get the orbital. So this is sort of the patterns that describes the state, and this pattern that describes the state is coming out of as a solution. Similarly, you have Gauss-Legendre polynomials. They came out of Legendre differential equation. The solution of this is this particular class of polynomials. Similarly, if we have Euler equations, we will get a different class. We have also associate Legendre polynomials. These are the one with the M in it. We are going to explore them next time. So they are particular class of polynomials, and we have Gauss-Legendre polynomials. They are particular class of polynomials. So we have many special polynomials that we can use that are coming, or they have particular pattern computed out of particular class of differential equations. Okay, now we're back to this. Why the quadrature method worked? This is the first question. The second question, would any quadrature points coming from any type or any special polynomial work in general with any function or not? Okay, so let's hear your answers about this. Okay, who wants to start the ball rolling? You can guess also as well. I mean, no harm to throw an answer in the air. I mean, is it? I mean, you can imagine. Okay, now we have particular quadratures that came from this type of polynomial called Gauss-Legendre. Would this number of points or this method, which gives me specific roots for these polynomials at a particular n, would work for all functions or for particular class of functions? Okay, so let's jump to the second question. Why quadrature methods work in the first place? Okay, anyone want to guess? Yeah, but you can guess also as well. I mean, by imagination, by intuition, why it works. Okay, so I don't know if people don't want to answer or they are not existing in the code. You have turned it to be a special polynomials. Okay, so I have a complete silence. Anyway, then I think it's okay. So I see an answer from Muhammad. Okay. Yeah. Okay, I see a first question from Minna. Yes, this is a question that I was asking. Is it applicable? What do you think, Minna, since you have mentioned this? What's your intuition about it? Okay, so the first thing, and when we are in the lab of quantum simulation, don't fear to answer or be afraid to answer regardless. I mean, spread out your intuition. Just tell it, inform us about it, because that's the way you learn. Because you try, if you fear because of don't want to say something wrong, I mean, you are gonna never learn about this. Okay, so we come to the point of Muhammad, the heat function. So okay, so what do you mean by heat function? You might also say it in the mic. Yeah, so now we are not talking about wave functions. We are talking about any types of functions, because wave functions, the wave function by itself is a special class of function. I mean, we regard them to treat electrons or anything. They have to be normalized. The wave functions have also to be orthogonal, because if you have distinguished states, so this is like a specific way to look at general functions. So you can have this e to power minus x as a part of our function. You can have it as t to represent a free particle. So that's a way. So the quadrature methods. Okay, the singularity is a different issue, Ananda. So the singularity is a different way to look at the function. So the singularity is the way that, okay, can you have, when you get the absolute limit of your function, can you approximate or evaluate the function at this specific point or not? So it's related to the continuity of the function and so on. You might still make a numerical integration for a function that has a singularity. You have 1 over x, for example. So that function, is still integrable. It's not impossible to integrate. So that's regarding this. So the weights are not variables. The weights are coming from the number. So that's a good point. So let's see the weights. So these are the polynomials. These are the points. So the points here coming as the roots of these polynomials. So this is a general formula to compute this. So from this you can compute the points, and then you can they are orthogonal. It means that if they are the n and m equals to one another, you get this coefficient. If not, you get 0. So this is the meaning of orthogonality. So the orthogonality will give you this canonical delta. So if the n and the m equal to one another, then at that sense you get 2 divided by 2n plus 1. This is like as a normalization. If not, this canonical delta will be 0. And then you get a 0. So the functions are orthogonal. The orthogonality is inspired from the dimensions. If you see the projection of the y-axis on the x-axis, you get 0. So the dot product of this is 0 because they are orthogonal to one another. They are perpendicular to one another. So similarly, the polynomials could be perpendicular or orthogonal to one another. So they have 0 overlap. If you made this integration, and then you get something with canonical delta. So here, if you got this canonical delta will equal to 0 if m doesn't equal to n, or equal to 1 if m equals to n. So this is a canonical delta. Now, after this, we want to get the weights. So the weights coming from a certain part of the function. So when we go to see the function, want to show you the weights. Let's just search for the weights then. These are the weights. So the weights are defined. You can multiply the function by a weight. So the weights is part of the function. And after you evaluate this, you get those weights. So these weights are distributed and computed from this formula. So next time we are going to explain them mathematically, because we have to show you, okay, you have the function, you have something multiplied by this function like exponential or anything. This term will act as the weight, because it's really the weight of the polynomial. So you see here, it is this part is acting like the weight of the Legendre polynomial. So if I make like this, then you sort of have these polynomials, and these are the points. Then you get the weights from here, from this normalization of this function that multiplied by the polynomial. Okay, so this is for this. This is, let's look to the chat again, because I lose the chat every time. Okay, yeah. Thanks, Ziad. So did I show? Then did I succeed to show the weights, the table of weights and the quadratures? Okay, so let's go again. Does this appear now? Okay, so these are the weights here. So the weights you compute with this formula. And once you compute this weight, if you multiply the weight times the point, the function evaluated at this point, because these are the roots of this polynomial, then if you sum, you get the approximated integral for that, because you have the function, you have this line, this line, this line, and then when you sum, you get. Okay, now we come to the question, why the quadrature method works? Because of the properties of the special polynomial. The special polynomial, the behavior of the function, just probes, is like making a sampling, probes the shape of the function that you would like to integrate. So not all quadrature methods will work perfectly with every function. You need to be mindful of the function that you are exploring. and studying. So if you have a sine function, Gauss-Legendre will serve you well. But if you have, for example, a polynomial that's not behaving rightly or behaving with exponential part, you might use, for example, Gauss-Legere polynomials. So Gauss-Legere goes with this. So the polynomial itself has to have the capacity or the pattern to go with the shape of the function that you would like to integrate. So it needs some sense, some intuition. Which data I'm integrating, which symmetries are already existing or presented in the system that I'm exploring. Based on that, the choice of the polynomials and their associated quadrature method, which specifies the weights and the points, will be determined. Yes, Mohammed. So yes, and no, it depends on the use case. So if you have continuous and bounded function, that's for sure you can use the numerical integration. If the function is not continuous, it depends on how you would you might divide it into parts. So you can avoid a particular part where the function is not defined. So there is many tricks, but if you have an bounded integration, so the numerical integration, you need to have a specific interval, and in this interval you have sort of a wall you start jumping from, and a wall you end, and then you want to sample in this. So the sampling part has to be smart, and in this sampling, you need to think, okay, which behavior I do have? I have, for example, sinusoidal behavior. Then maybe I will use something that goes with sinusoidal. You have also sine and the cosine behavior. And we have seen the Gauss-Legendre have this nice way of doing things. So they can sample the data. Let me just show you an animation. Trapezoidal rule there. Then you have approximated numerically using trapezoidal rule. But now the trapezoidal rule, you have to really squeeze and choose many points in order to make this interval smaller and smaller. But then with the smarter choice of the quadrature, you sample the function. So you can choose this point, and then a point in between. And because this weights goes with the behavior, then once you evaluate the function, you multiply by the weights, you are sort of emulating the behavior of the function, and then you can compute successfully the area under the curve. Then you make it bounded. It's bounded because it's a numerical integration has to be done within a specific interval. Otherwise, it will be analytic. Analytic, it means that for any interval, your integration, you get a formula that works all the time. Yeah, I'm just showing another animation. So bear with me. Yes, now it appears. Okay, so I have to just make it start from the beginning. Okay, let's see if I can succeed to do this. Yes. You see now, this is a given function. And you wanted to integrate from here to there. So this is your area. Now you sample. You see the function is sampling the behavior. So So it goes here by the weights and they make this sampling, and then you can approximate the integration using less number of points. Now it's gonna be repeated. Again, this is the area under the curve. We have a bounded area. It's a bounded integration. 4 points or 5 points here are used, and the polynomials are sort of emulating the behavior. They are coming to probe the shape of the area, and then by that you can make your approximation. Okay, so let's see the chat and check the questions. Yeah, thanks, Mohammed, for asking a question. I mean, all the time asking great questions is always what pushes us to learn. So that's nice of you that you are asking questions. Otherwise, we will have a very silent space, and then we have to make special polynomials to sample, which means that we have to make a sort of a random function and then ask everyone randomly what he or she already has learned in the past half an hour. Okay, let's choose Ziad. Pick up any person you would like, and then we can ask him or her. Okay, Ziad wants to be merciful on people. Okay, that's nice. Okay, Abdullah. Okay, Abdullah, what you have learned so far? Okay, so apparently everyone or some people are really just not attending and having the session open, and that's it. Okay, so pick up anyone as yet.
So I think Gamal can rock the ball. Gamal Munib.
Okay, so Gamal, the mic is yours. Okay, guys, don't fear. I mean, we are discussing things. I mean, we are exploring together. I mean, if you are now shy, it means that in the hackathon you might not be able to present at all. If you have this kind of being shy here and you don't want to ask questions, how you are gonna even be good at presenting stuff in projects and work in use cases? I mean, that's okay. So, okay.
Okay.
Gamal is escaping. Okay, nice escape, Gamal.
What about Abdurrahman?
Abdurrahman. Okay, yeah. Abdurrahman, where are you? Okay, then we might ask Omar to give his opinion about the last half an hour.
Dr. Taha, I'm afraid I didn't hear you well. What was the question again?
No, we are asking about what did you learn and your reflection about the session of the numerical integration.
Yeah, okay. So I learned about the trapezoidal integrations, or about the noise background. Okay. I found the session is very, very useful. And of course, it will be needing more study just to be able to make things concrete in my mind. But thank you very much.
Yeah, thanks, Omar. Definitely, that's first session. So we are getting this. We are just passing the discussion to one another in order to learn, because it's just starting the ball rolling. I mean, what we are going to see next time is more the expansion coefficient, so we are taking it slowly. Abdullah, please go ahead.
Assalamu alaikum. In this session, I understand how to apply some of my knowledge of calculus in a different field. Also, I recently entering in the topic of solving differential equation using machine learning, and this session was good enough to review some of my information and give me different knowledge in approximation integration.
Okay, so that's nice to hear. Thanks for your input. Also, thanks, Omar, for your input as well, because some people are using there is also packages that are being used out of the box, and then they don't show what happens under the hood. Okay, Ahmed, please go ahead.
Really, I have a question about the Gauss Legendre function. If we increase the number of n values, it will vary around the exact value, or just the exact value is the upper limit for the calculation? Is it is the question clear?
Yeah, definitely. So that's a good question. So typically you should get the exact value. However, if you increase the number of points too much, that has to be tested within use cases. So I would imagine, I mean, this is of course has to be shown. We can test it now, that you might get some noise and some oscillations in noise because of the increasing the huge number of polynomials that are sampling. But this might happen not so you already converge your results. So because we have seen it, we had 3, we had 4, so we were oscillating actually around the exact value. So let's
it oscillates. So
is not. I don't want to be precise about oscillation, but we are making variations around the exact value, tiny variations here. In this example, let's see.
Okay.
We have here 3 points. And here we have 5 points. Of course, we can make now, for example, 10 points. Then sort of we are getting more, we are converging more decimal points. So if I go here, let's see how many decimal points did we converge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there 1, 2, 3, 4, 5, 6, 7, 8, 9. So up to 8, we have converged 9 digits. Here 7, 6. Yeah, we have here about.
So if we increase it to 20 or even 50,
yeah, you will get. Yeah, you will get tiny bit of
conversion
of variation.
Also,
yeah, of course you will get. Yeah, okay. Let's see now. So convergence you will get all the time because now your integration is complete. But then the idea is that you have certain residual of digits here that is gonna fluctuate. To be more precise, yes. Yeah. So after the 10th digit or so, because it's you see it's even now start to converge more. So we have now 6060 here. Still the 4, we are talking about the 13 or 14 digits of precision. So if I make like this, I make 50. So we have even converged before the last digit. The problem about special polynomials that depending on one note about this, we might do things that's related to
someone share a wrong screen.
I think so. Yes. Yeah.
Jomana, you are sharing the wrong screen there, Jomana.
Yeah, you are sharing your screen, Juman.
I can't.
Okay, so because of the time, okay, let me just okay, now I'm forcing my screen. So we have to be aware of something here. Depending on the algorithm that's used to compute this polynomial, sometimes the algorithm might blow up at certain limit. So sometimes when we make certain evaluations, we have to make sure that our algorithm doesn't explode at higher degrees, at higher n. So that might be the case if you, for example, with 100, then you check still now we have a good convergence. So that's not the case, but for some function, the algorithm might have issues. And this has happened in advanced polynomials and advanced functions like Wegener-D matrices. In the Wegener-D matrices, if the L and the M, there is some degree and order for this because they are function of spherical harmonics. At certain limits, the algorithm that's used and the precision that's used in the algorithm might not be enough, and then you might get sort of a very fluctuating results. So not correct because of the algorithm that's used to compute this specific type of functions. So here we get tiny fluctuations, but it's a good convergence. So it's still converged, but the tiny fluctuations happened at the last few digits. There is explanation for this. It might happen because of the precision used in this algorithm. This is why in our package, we try to take care of this definition. So all the time we define up to 16 digits of accuracy, so we can get the same precision all the time. But if the algorithm is taking 10 digits only and dropping the rest for the performance reasons, then you might get some fluctuations after 10 digits, for example. But now what we see is we see, I think, very good 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, yeah, up to 15 digits. That's very 14 digits after the decimal point. I think that's enough. We can tell it's that. So it depends on the use case. So what type of polynomials do you have? The algorithm that you are using to compute the polynomial. Some use cases might force the researcher or the engineer to use specific algorithms to compute these polynomials. Otherwise, one algorithm, they are equivalent, they all can give the same results. But at extreme cases where you use very high degrees, the algorithm might blow up and then brings for you wrong values. So that's to be checked with the formula and sometimes analytically to make sure that's not the case. So try with 1000. And then if we try those 1000, okay, still we get the same. So yeah, so I think that behaves for this use case, that behaves nicely. Most of the time, these polynomials, because they are sort of they take sort of sinusoidal fashion, they will behave nicely. But for example, for Gauss-Leger, this type of polynomial sometimes need careful computations because they go as exponential, so they go like this, and then you need to be careful about the number of points where you are getting at a very high x, for example. So yeah, that's the answer I can tell. Depends on use cases, and of course the algorithm that's used in computing the special polynomial.
Okay. Thank you for clarification.
Yeah, I'm sorry, but this also depends on the use case. So if sometimes you might have a very nasty function, and for example, there is particular class of polynomials like Jordan, D Wegener matrices. These are have to be done carefully. There is transformation that happens with particular polynomials, and this transformation might explode after a certain limit, like spherical harmonics. When we do there is a famous use case when I was doing my PhD where we use, for example, double precision in Fortran to compute the transformations from the body fixed to space fixed. But then they use higher angular momentum numbers, and at certain limit, the coefficients start to behave strangely, and then you get very wrong matrices, sometimes ill-conditioned. It's not unitary anymore. And one of these reasons might be the precision that's used. So we moved with a nice, much better algorithm that can leverage the quadruple precision. And then the real use up to 8 digits. In Fortran, quadruple will get the full 16 digit, but then that comes on the expense of in the performance and then the memory. However, that potentially might solve certain issues related to this type of unitary matrices that might appear. We're talking now about, for example, few k by few k in size. So that's extreme cases where we see, but here we see very simple sign function. So it might not be a good use case to really push the limit for this Gauss-Legendre quadrature. Okay, so let me check the chat again. Right, so the integration, yeah, like you are simulating the integration itself, which could potentially be a solution of an equation or help you to find the solution of an equation. And the second question from Mohammed about the weight part of the equation, you can treat it like weights in the nodes of neural network. It's similar. It is similar for sure. You might get overfitting, yes. Sometimes if you, that's not here today, but that will come later. When we do an expansion using, for example, a particular class of polynomials, the question is how many terms do you need to expand for? So for example, you can use numerical integration using 5 points, or you can use numerical integration using 16 points. But then when you increase the number of points, you are learning more about the type of data that you are handling. So the points that you have entered in your evaluation, you will get the same. So you might get the same points up to 16 digits of precision. However, the points in between, because of the high oscillation patterns of these special polynomials, you might not get them in a good way. So there is always a trade-off. Do you need more to evaluate your potentials on these points, or do you need a good interpolation in the points in between? So that also comes by testing. There is no universal rule in this. You have to test by hand and see. But what you say is what's happening indeed. Okay, so I don't want to take much time from the lab because Ziad is quite motivated. He have made many examples out of these, so you are gonna see more examples with him about this, and also more and more numerical integrations. Hopefully now the theory part and the visualization part is in our mind. Next time we are gonna have a use cases, about much better use cases, because they will be more sophisticated than this simple type of functions. And after that, we are gonna dive deep more into the math part, because the quantum simulation is also we have to get more fluent in particular class of polynomials, functions, and solutions of differential equations. And after that, we are gonna move slowly towards the Hamiltonian and how to build on them in quantum simulations. Okay, so do you have any questions? Okay, so just a quick recap. Who found the session useful today, or got some new insights? Okay, let's see, 2, 3, 4, 5. So we assume that we have 7. Then the rest are experts already in the field. That's great. Okay, Mohammed, please go ahead. Okay, so you you are raising your hand just to tell that you gave your reflection about the session. Okay, then that's it for the day. I'm leaving now the mic with Ziad. Okay, Ziad, the floor is yours.
Okay, Mr. Thomas. Okay, Dr. Fan. So just let you rest for 1 minute and then I'll start.